Okay, welcome to topic 7/17. Just in case you ever wondered what all those numbers meant, 7 is the standard level, what they call the core material, and 17 is the additional higher level. They get mixed up. The material gets mixed in together. This way we can teach it one topic at a time. If I taught it 7 and then 17, you'd see all the same topics, but at a higher level later on in the chapter. So I think it's better to do it this way. But anyway, back to the idea of you bringing to the table what it is you remember. So, equilibrium. What is meant by the term equilibrium as it applies to chemistry? Press pause, and I want you to take maybe a minute or two and brainstorm some ideas and write them over here in this spot, right up at the top. Go ahead. Okay, so I assume you've done that at this point. So let's write some of the characteristics of equilibrium that we've learned. One is the only definition that you've learned to this point, which is that the change in delta G, I need more symbols. How many delta? Come on. There we go. Delta G equals 0. That's one thing you've learned. What else? What else do you remember from 10th grade? You might have it up here, actually. That is that the rate of the forward reaction equals rate of the reverse reaction. And that has an implication to concentrations. Concentrations will stay constant. Now, these are like things you learned in 10th grade that have to be by rote. For those of you who have any calculus background, it makes a lot of sense that if the concentrations are constant, that the rates will have to be the same. Take derivative of two constants, you'll get equal rates. Or equal rates will give you concentrations that are constant. Delta G equals 0 is a definition saying that the reaction is neither spontaneous nor non-spontaneous at that moment. Oh, Bella, Alex asked me to give you a shout out, or actually just to give you a hard time. I'm not going to do that, so don't worry about it. It's all good. Alex, we can talk about it later. Anyway, the idea that delta G equals 0 is a mathematical thing that we will tackle toward the end of this chapter. Now, a dynamic equilibrium, which is the kind we're going to be speaking of mostly this unit, is one that is, well, what do you know about dynamics in music? Take 15 seconds. I know most of you are involved, many of you are involved in musical groups. What are dynamics? I know dynamics is volume, but what do dynamics do? What is it possible to do with something that is dynamic? Press pause, take a second. Okay, a dynamic equilibrium is specifically a changeable equilibrium. And we're going to see that this year, shortly in this topic. So a changeable equilibrium, and not only that, but one in which the reactions involved never stop. Rate forward equals rate reverse does not mean that they're both equal to 0. You look at a beaker at equilibrium and it will look like nothing's happening, but in fact both reactions are happening at the same time. Think about simple stuff like, I don't know, I've got some saturated sugar water because I feel like making some really sweet syrup. I look at it, doesn't look like much is happening. The truth is that at the surface of those sugar crystals, there is some degree of dissolution, but at the same rate, the sugar that's in solution is precipitating. So when I look at it with my, naked eye, it doesn't look like anything's happening. Yet both reactions are still happening. So the reactions don't stop. They just happen to go at the same rate. And so to our eyes, it looks like nothing much is changing. Nothing is changing. It just doesn't look like anything's happening, but there is. It says here we'll do some predicting in a little while. That's coming up actually on a DVD with the kids back from 2014 that you'll have some fun with. But first, we have to develop an example of dynamic equilibrium. We're going to start with a pretty easy one, phase equilibrium. And this comes out of the Noyce textbook. What can you say about a liquid-vapor equilibrium? Write down your best explanation, and don't forget to include a closed container as part of your description. Okay, who's got a Poland Spring water bottle? I'm not endorsing any brand of water bottle who has a closable water bottle. Excellent. Okay, hold it up. This is a closed container, and if you wait long enough, you will have a liquid to vapor equilibrium. Describe what's going on inside that equilibrium in your groups of 4 or so. Now, press pause. Okay, now take stock of what everybody else has said, and so please take a moment and have a discussion. Okay, great. So now here's the question. There is only one way that you can change the ratio of liquid to vapor molecules in that closed water bottle. What is the way you change that ratio? Now, you may think that by having a bigger bottle, you can change the ratio. You can't. You can change the number of vapor molecules that seem to be able to escape into the atmosphere, but it's not going to change the ratio. All right, I think you might have it. The only thing that can change the ratio is changing the temperature. And that's what we're going to focus on and how we can describe that on a molecular level. Changing the temperature. So think about this in terms of particle velocities. At lower temperature, what's the particle velocity like? Therefore, what might that do to the evaporation rate? And at higher temperature, tell me about the particle velocities and therefore something about the evaporation rate. So you should write something like that down. You can press pause again so that you can write something down. All right. Now, something might come in handy in here. What might it be? A Maxwell-Boltzmann distribution. So what is this showing us? So think about evaporation. It's not a chemical process, but think about it as a physical process with some sort of energy of vaporization or evaporation. Think about it somewhere around here, like any old activation energy. There's some energy you need to get these molecules to escape. I'll just put my cursor right there. I can't draw so easily on this document. So put my cursor right on the x-axis where I'm suggesting to put it. Look, at the colder temperature, only these molecules can evaporate. But you increase the temperature, and more of the molecules, more absolute molecules, and more of a percentage of the entire sample, they can evaporate. And so you change the liquid vapor ratio that way. So Maxwell-Boltzmann can really be used to show a whole bunch of things. It's really kind of very useful. So what you should do is you should make a mark for evap. Okay, I just put evap down here. And then make a line. And then draw in shading with hashes, whatever. You can kind of do slash marks one way and then slash marks the other way for the warmer temperature. You want to show that only these molecules can evaporate under the colder temperature and all of these molecules can evaporate under the warmer temperature. That's what you're being shown. So that's a good first example of equilibrium and how you can describe it on a molecular level. What you're going to do now is you're going to go on to the DVD, which will start you off on page 46, talking about Le Chatelier's principle. Henri Louis Le Chatelier and his principle. So enjoy that and see you later.